All right, I think we're ready to get going here. We want to give the speakers as much time as possible, so welcome to our first session for Tuesday. We got a great lineup of speakers as always. As I was sitting through the breakfast speaking, I don't know if you guys ever go to the other side's conventions. I like to hear both sides of the story on everything, just so as a politician, I'm always informed. And I noticed the one thing that makes sense to me is the difference between their PhDs and our PhDs is I see people nodding off while their PhDs talk, and our PhDs seem to have a lot more life and a lot more passion and a lot more excitement. So I know we've got a good lineup here this morning that's going to keep you awake and give you a lot of good information. So our first speaker this morning is George Taylor. George Taylor is president of Applied Climate Services of Corvallis, Oregon. In 2008, he retired from Oregon State University, where he served as state climatologist for Oregon for nearly 20 years. So welcome, George.
Thank you, Mike, and thank you. I accidentally deleted my title slide, which has my name on it. And it had that picture too, but it's only a title slide. It's a pleasure to be here and to be with two of my friends who are also heroes of mine, Roy and Bill. As state climatologist, one of my stated roles, and it was part of the charter of my office, was to put current weather and climate into historical perspective. And that's what I tried to do at Oregon State, and that's what I still try to do. I'm also driven by an incentive from the Bible, and it's the book of Ecclesiastes. Ecclesiastes is really Solomon going around the world and making observations and essentially saying, "This have I seen," and therefore, and making conclusions. So I'm going to present some information, some things that I have noticed about weather and climate data, long-term data, and I have come to conclusions about what causes those and what affects those. I'll also reminisce about something that happened to me in the early 1990s. I went to an AMS conference. It was one on hydrometeorology. It was in Anaheim, California, and I heard a talk by a fellow named Bill Gray. Bill Gray, in his talk, talked about long-term cycles which affected hurricane formation and showed cycles on the order of roughly 50 to 60 years with an up phase and a down phase. And he suggested in the early 90s that we would soon be moving back into an active phase in Atlantic hurricanes. He gave me incentive to go back and look at weather and climate data for the Pacific Northwest, temperature, precipitation, snowfall, and so on. And I noticed similar length and similar coincident, quote-unquote, cycles in the Northwest. In the mid-90s, I spoke to the University of Washington scientists about this, and they saw the same thing, and they gave it a name. They called it the Pacific Decadal Oscillation. And it's something that seems to explain a great deal of the variation in weather and climate throughout the Northwest and in other parts of the world. Some people question whether it's really the source or it's really an effect, and it's probably both. I think ultimately the PDO may be an effect of changes in something like solar radiation, probably solar radiation itself. But in turn, there is an effect that these changes in the tropical Pacific have throughout the world. So I'm going to show some of those now. This has much too much text in it, but up at the top are the two phases of the PDO. On the left is the the positive or the so-called warm PDO, which tends to coincide with El Nino events in the Pacific, and warm anomalies in the eastern tropical Pacific, cold anomalies, and a very deep Aleutian low in the northwestern Pacific and the northern Pacific. The other phase of the PDO, which is really what we're in right now, is more characterized by La Nina conditions with cool anomalies in the eastern tropical Pacific, warm anomalies up in the north, and more zonal flow and less of the deep Aleutian low. This is a time series done by the University of Washington back to 1900, showing the positive and negative. Again, the periods like 1920 to 1945, mostly in the positive range, the red, and coinciding generally with El Nino events in the Pacific. Mid-40s to mid-70s, generally in the blue. The negative PDO, the so-called La Nina, tended to dominate. a very rapid change in the mid-70s and back to a positive PDO. And then from the late 90s until now, there's been some flip-flopping, but more blue than red since the big El Nino event of 1998. If we compare this with, for example, U.S. temperatures, and this is from the Goddard Institute of Space Science, we see that those 4 periods in the last 100 years coincide generally with relatively cool temperatures up to 1920, warming in the 20s, 30s, and early 40s, coinciding with a positive PDO, cooling again in the next period, followed by warming since 1975. And of course, this is a few years old, so it doesn't show the cooling in the last few years that's coincided with that reversion back to the negative PDO. Several people have put together a long-term time series of PDO. This is from Franco Biondi of NOAA, based on tree ring studies in California and Mexico, with estimated PDO back to the late 1600s. The point of this is that the PDO seems to be a phenomenon that exists throughout the paleo record, at least as far back as we can see. Alaska climate has had a very, very significant impact from PDO. And when I say it has an impact from PDO, what I really ought to be saying is that it coincides with changes in the PDO. I know there was some discussion yesterday about cause and effect, and correlation does not necessarily mean causation, but in this case, the fact that these things are so coincident certainly appears to be the case. This is summer average, May through September average PDO, negative up until the mid-70s and positive after, with the average sea surface temperature anomalies for both periods. Again, in the negative PDO, generally warmer temperatures in the North Pacific, cooler in the tropics and subtropics, and then in this period, just the opposite. This was a very, very dramatic change in 1975-76, more dramatic than any we've seen in the last 100 years. One of the problems with something like PDO is it's not always easy to spot when it switches from one mode to another. But in the case of 75-76, there was a major change within the span of 1 year. And the effect on temperatures in Alaska was very, very dramatic, as you can see here. This is mean annual temperature departure for Alaska back to 1949, and you can see the negative anomalies in the mid-70s quickly changed to positive anomalies thereafter and remained that way through the beginning of the 21st century. Brian Hartman and Gerd Wendler of the University of Alaska at Fairbanks wrote a paper that described the effects of that 76 climate shift. And I apologize for all the text here, but I can summarize pretty quickly that after the shift, there was an intensification of the Aleutian low. That's point number one, which causes a real strong advection of relatively warm air from the south. It also brings in additional moisture. So the regime in Alaska changed from relatively cool and dry to relatively warm and wet. Next, there was a frequency of higher wind speeds, which reduced the number of temperature inversions, which also tended to raise the temperatures. And finally, there was a reduction in total snowfall, even though there was more precipitation because there were higher temperatures. So all of those really changed in the mid-70s when we moved from one regime to another. In the Pacific Northwest, where I live in Corvallis, Oregon, there's also a very strong effect in several ways. These are long-term temperature trends at stations in the northern part of the coastal Northwest and in the southern part, which is southwestern Oregon, northwestern California. And I want you to focus on this section right here. What we see is a lot of interannual variability, but a general trend towards warmer in the 30s, 40s, cooler in the 50s, 60s, and then warming since the 70s. So certainly some hints of something that looks cyclic. If we plot those with a PDO, in general, the PDO and the temperatures coincide. So most of the temperatures in this negative PDO early in the record were were negative compared to the long-term trend. The temperatures in the 20s, 30s, and early 40s were higher, and so on. So we really see that throughout the record. This is one of our more reliable long-term stations in my current hometown, Corvallis, Oregon. And this really typifies what we see in rural stations in the Northwest. A generally warmer period in the 20s, 30s, and early 40s. This was the warmest period in the last 100 years, and the warmest decade was the 1930s. The warmest year was 1934. It was cooler in the 50s, 60s, early 70s, and then warmer thereafter. So this really typifies what we see throughout the Northwest. And again, it coincides generally with the warmer period in the positive PDO period, 20s, 30s, early 40s, cooler with a negative, and warmer here. And we've actually seen a reduction in temperatures in recent years. We also see some pretty strong effects on precipitation. These are precipitation anomalies, annual precipitation compared with the long-term average. So a red year is a dry year, a red symbol is a dry year, blue is a wet year, and the length of the red or the blue represents how dry or how wet it was. This period with a positive PDO was generally dry. About 3 out of 4 years were drier than average. The period from the mid-40s to the mid-70s was generally wet. This period was generally dry, and then beginning in the late 90s, we moved back into a largely wet regime, a couple of dry years, but a lot more wet years than dry years. So precipitation effects are pretty powerful as well. One of the big controversies, and it actually led to some of the controversy involving my job, had to do with snowpack. Phil Mote and co-authors from the University of Washington published a study in 2004 that suggested that the snowpack was declining by, in some cases, more than 50%. And the implication was that it was because of anthropogenic global warming, and it would continue. Snowpack is essential to water supply in the Northwest, so that would be a big bummer. What the University of Washington group was looking at was snowpack conditions from 1950 through 1997. And what I plotted here was snow water equivalent. That's the amount of water in the snowpack on April 1st, which is usually the deepest time for snow. And if you use that data, this is a Willamette Valley drainage station that's at about 4,500 feet. What you get over that 47-year period is a loss of about 43% if you fit a linear trend to it. Clearly, there's a downward trend in that. The problem is we have a lot of data that's older than 1950 and quite a bit of data that's more recent. And if you do the Paul Harvey thing and look at the rest of the story, thank you, Paul, we get no trend at all. This is the same station, Roaring River, for the whole period, 1929 through 2006. And this doesn't even include the very, very wet winter we had very snowy in 2007, 2008, and also, 2007, 2008. We get no trend at all. And it's true of pretty much every snow course station in the Northwest. This is another one. Partial record, 38% loss. Full record, no trend. This is the oldest one we have. Bumping Lake, Washington, goes back to 1915. 38% loss. If we start at the snowiest period in the last 100 years and end during a drought period, we get a loss. If we take the whole record, we get neither. And in fact, what I see is something that seems to coincide very nicely with the PDO index. That curve there is just meant for illustration. It's actually a fourth order polynomial, but what it shows is higher values in the 40s, 50s, early 60s, coinciding with this blue period. Lower values here, lower values here. Basically, during the red years, you tended to get less snow, and it makes sense because these years are drier and milder. So dry and mild is really not a good thing when it comes to snowpack. Fisheries, there have been some very, very significant effects on fisheries. Let's say the politically correct viewpoint is that what really causes salmon to decline are the 4 H's, harvest, hatcheries, habitat, and hydropower. And yet I see a lot of long-term variation that fits really nicely with PDO. In fact, I used that to make a prediction in the late 90s that we were going to see a resurgence of salmon in the Northwest because I believe we were moving into a different PDO regime, and indeed, that's exactly what happened. Here's fall Chinook and spring Chinook runs in the Columbia River. This shows a PDO index, positive index until the late 90s, and then negative or barely positive since then. And then the line here shows salmon, and salmon all of a sudden went from being endangered and worried about to being abundant, just in the span of a couple of years, coinciding, and what a coincidence it is, with a change in the PDO. But that makes perfectly good sense as well. Mild and dry is pretty bad for salmon. It means the rivers have less water, the temperatures are warmer, and it also coincides with different upwelling patterns offshore. So the negative PDO is beneficial in many, many ways, and I think this is the key to salmon returns and salmon survival. This is another fisheries parameter. It's copepod abundance on the bottom and PDO on the top, back to 1996. Again, coinciding beautifully, just as you would expect, because it has some physical basis. The Arctic, Willie Soon showed a picture, and it was really this picture. It's Igor Polyakov's Arctic surface air temperature anomalies, published in 2003, showing the rise here, the fall, the rise, and I look at that and I see PDO. Warming coinciding with the positive PDO, cooling coinciding with negative warming. And Willie says this is caused by changes in solar radiation. He may very well be right. And this may be caused by that as well, but these are certainly coincident. Now maybe this doesn't cause this, maybe they're both caused by the same thing, but I think there's a similar phenomenon that's going on. One of the really interesting papers that I've seen has to do with Glacier Park, which is one of the poster children for global warming. Thank you, Al. A marvelous paper that I highly recommend by Greg Peterson and co-authors in 2004 in GRL, which looked at decadal scale climate drivers and glacial dynamics. And here's an example. Without a doubt, the glaciers in Glacier Park have melted since they were first observed. And even in the last 90 years, here's Grinnell Glacier and in 1910, and here's 1997. The way that most glacier people characterize the size of a glacier is by the elevation of the terminus. So right here, the terminus was at that elevation, and here it's way up here. So clearly the terminus has risen, the glacier's gotten smaller. And it's even more so if we look at early photos from the mid-19th century. What Peterson and co-authors did is they examined long-term trends based on glacial moraines and other things, and looked at when and how the glaciers had changed, basically when they melted. Now I didn't really like this plot very much. This is distance versus elevation. So I took their data points and converted it to a time series. I'm a time series guy. What can I say? So Jackson Glacier, beginning in about 1860, there was a slow die-off. One of the things that they pointed out is 1860 is about when we started taking measurements of glaciers and photographs, and this was at the end of the Little Ice Age, and they said probably the glaciers were as big as they've been or bigger in the last 1,000 years. Well, they began to slowly die off and slowly melt, beginning in about 1860, and then beginning in the late 20s, they started melting like crazy. And you can see that about 80% of the loss in the glacier occurred in the span of about 10 years, between about 1928 and the late 30s. Clearly, there has been some additional loss since then, but most of it occurred in that period, which was a very dry and warm decade. The Agassiz Glacier is even more extreme, with a higher percentage of the melt in that same period of time. And this is their time series of advance and retreat of glaciers back to 1700. The blue coincide with periods when the glaciers were growing, advancing, and the red when they were retreating. So here's the tail end of the Little Ice Age, big surge in the early 1800s, and then generally more red than blue during this period, but with most of the decline, the rapid retreat in the 20s and 30s. Since then, there have been alternating growth and decay, or ablation, as the glacier guys call it. They also put together a reconstructed PDO index, and here's the significant thing on the right. Snowpack fluctuations in Glacier National Park exhibit a significant relationship with the PDO. PDO and local May 1st snow water equivalent are negatively correlated with an R of 0.76. Now, in the kind of climate stuff that I do, when we get an R value of 0.76, we break out the champagne and celebrate. That's a pretty big deal. And they're saying the PDO is primarily responsible for those kinds of changes. We see the same thing in the North Cascades. Real quickly, this negative PDO period, the 50s, 60s, early 70s, actually coincided with glaciers advancing. They've declined since then. And those who like to cherry pick will take 30 years and say, look at that trend. And I say, yeah, but look at this. In conclusion, there seems to be evidence that the PDO signal is a constant. It's a permanent feature of the climate system as far back as we can see. A typical period is about 50 years. This seems to vary, though. It's not a clockwork kind of a cycle. It's probably a quasi-cycle. There is certainly a close tie-in with ENSO phases, a strong regional signal, not just in the Northwest, but in broader areas. And I believe that PDO changes correlate well with variation in temperatures over the last century, not to mention precipitation and snowpack. Thank you.